Okay, so welcome back to another video. So in today's video we have the following complex expression, the ith root of the square root of I to the power square root of I multiplied by the nth root of I to the power m. So yes, we got this. It's nothing too complex. Don't feel so intimidated with a bunch of i's and then radical symbols. So basically, the way we're really going to tackle this is just convert some of the square roots into rational exponents, and then use some polar forms to convert some of these values, and then hopefully from everything from there, it's going to make things easier to help achieve our reduced simplification expression. So let's get started. We'll focus on the right-hand expression later. I really shouldn't say expression, but this constant rather. We'll deal with this later. Complex number. Well, we'll focus on the left side of the complex number first. So what I can do is that I can actually rewrite this. So basically, we can write this as a rational exponent. So this is the same thing can be written as the square root of I to the power square root of I, and then for rational exponents, it's 1 over I, but you don't usually want to do that. You don't want i's in the denominator, so what you do is that you can just multiply and divide I. So it would be I squared in the denominator, that'd be -1, and so I on the numerator, so we just get that as negative I. Okay, and then of course we'll just multiply this with, I'll write the exponent as the rational exponent. So this is just I to the power m divided by n. So now we know that the square root of I is actually just equal to I to the power 1 over 2, right? So what I can do is I can take that complex number I, convert that from what we see from the complex plane, and treat this as we write it in polar form, and I is actually equivalent to e to the power I multiplied by pi over 2, and of course multiply by 1/2. And of course, if I were to multiply this out, I get e to the power I pi divided by 4. And continuing forward, we know that if I use Euler's formula, I can rewrite this polar form in terms with evaluated of the cosine and sine. So it's basically the formula is cosine of x plus I times sine of x for some input x of e to the power I times x. So of course here we have our input would be pi over 4. If we plug that pi over 4 into our input, we get cosine pi over 4, which is just the square root of 2 divided by 2. And then plus I times sine of pi over 4, which is just the same thing, the square root of 2 divided by 2. So now then we have that the square root of I to the power square root of I. So what I'll do is that for the base, I'll keep it in its polar form. So that means it's just e to the power I times pi divided by 4. And then for the exponent, I'll write the evaluated input up from using Euler's formula. So we have the square root of 2 divided by 2 plus square root of 2, or I times square root of 2 divided by 2. And if I do the multiplication out, I get that it's e and then to the power, so we have I times I is negative. So that means this negative will, I'll move that to the front. So we have the square root of 2, then multiplied by pi, and then for the 4, so that means divided by 8, and then plus I times square root of 2 times pi, and then divided by 8. Okay, so now we have that. So then next it would be that the square root of I power square root of I, and then to the negative I power. So we have that. CE, we're just plugging back our substitution. So let's see, 8 and plus I square root of 2 pi, and divided by 8, and then to the power negative I. Okay, and now if I just continue writing this forward, then we have that this is, so let's see, e I to negative I is negative I squared, so that's 1, and then this will be a plus, so we have e and then square root of 2 times pi divided by 8, then plus I times square root of 2 times pi, and then divided by 8. Now, of course, continuing forward, I can, since the exponent, we have sums, what we can do is we could separate the bases out and treat this as multiplication. So we have e to the square root of 2 pi 8, then multiply with e to the power I times the square root of 2 times pi divided by 8. And now for this term we can write it out continue writing out using Euler's formula. So let's see, so this will stay on the outside, 8, and then multiply with, so use Euler's formula, we have cosine of square root of 2 times pi divided by 8, then plus I times sine of square root of 2 times pi divided by 8. Next we have that, so now let's focus on our I to the power m divided by n. So now I to the power n divided by n, of course we know that I is simply just equal to, in its polar form, e to the power I and then pi times 2, and then multiply with m over n. And so therefore we have that this is just equal to e to the power I, and then what is it, pi times m, and then divided by 2n. If we were to combine stuff together, then we have that the I root of the square root of I, then times I. I should write that a little bigger. I square root of I, and then the power I multiply with the n root of I to the power m. Okay, so now we have e to the power, so this is square root of 2 pi divided by 8, and then we just substitute cosine of square root of 2 pi divided by 8 plus I times sine square root of 2 pi then divided by 8, and then we multiply this with our now e to the power I times pi m divided by 2m. So I'll just write it out in its polar form. So it's cosine of pi m divided by 2n, then plus I times sine of pi m divided by 2n. So now from here we can actually use the FOIL method, and so that means, let's see, we keep the square root e to the power square root 2 pi divided by 8 on its own. We'll just now do we'll do our FOIL. So we have cosine of square root of 2 pi divided by 8, then multiply with cosine of pi m divided by 2n. Okay, next is doing the outside, so we have plus I and then cosine of square root of 2 pi divided by 8 multiplied with sine of pi m divided by 2n. Okay, I'm gonna go to the next line. So now next would be over here. So we have plus, so it's I and then times sine of square root of 2 pi divided by 8 multiplied with cosine of pi m divided by 2n. And now next is I times I, so we have a minus, so I squared, so it's minus 1. So then this is sine of square root of 2 pi divided by 8, and then times sine pi m divided by 2n. Now how about I separate the real part and the imaginary parts. So let's see, so now of course we still have the same thing from over here. This is e square root of 2 pi divided by 8. Also keep this in brackets. So if we separate the real parts, we have cosine of, basically just writing the same things over again, we're just separating some stuff. Pi m divided by 2n, and now we have the real part over here, so this is minus sine square root of 2 pi divided by 8 sine of pi m divided by 2n. How about this? I'll draw another second bracket over here, and then plus I times our now this piece is with the imaginary piece, so square root of 2 pi divided by 8 sine pi m to n, and then let's see, this is added with sine of square root of 2 pi, yeah, and now multiply with cosine of pi m to n. And now that last part, really, if you use your rules of angles and the sum and sum/differences of the angles, you'll get that cosine, sine, it's equivalent, or subtract with sine, that's actually equivalent to cosine of the two inputs. And if we have a cosine times sine plus sine times cosine, this is basically just sine of the two inputs. So now we have so basically our final answer is, so it's e square root of 2 pi divided by 8, and then it's cosine of square root of 2 pi divided by 8, then plus pi m divided by 2n, and then we add this with the imaginary unit multiplied with square root of 2 pi divided by 8 plus pi m to n, like so. And there we have it, the final answer, aka the further reduced simplification of our given right over here. All right, that's pretty cool if you ask me.